Hi everybody, welcome to this SIPROTEC Process Bus top-level qualification training. My name is Yelitza Rojas and I'll be guiding you through this 4 series of videos where we will discover the fundamentals of the technology. We'll see some network architectures, the main features of the Process Bus client and merging units, and at the end we will learn how to select the devices in the SIPROTEC 5 configurator. So let's start with the fundamentals. The first question is, what is Process Bus? And to answer it, then we can see a conventional station, what we do today. So we wire the complete information from the yard using copper cable to every one of the devices needing the information. What we want to do with the Process Bus is replacing all this copper cabling by optical Ethernet communication networks, and for that we need some special devices called merging units. These merging units are then responsible for the acquisition of the current and voltage of every bay, the digitalization of the values, and the publishing of this information to the communication network through the so-called sample measure values. Those devices, the merging units, are called the servers because they are publishing the information, while the protection and control devices are called the client devices. They are subscribing to the information in the network. In addition to voltage and currents, also the merging units are able to collect other type of information and transmit it to the network. For the sample values, we use the IC 61850-9-2, and for all other type of information, then we use the IC 61850-A-1, especially goods messages for the transmission. So now we will see the technical principles of this technology. When we care about them, then we will develop successful projects with Process Bus. And then we talk about 3 key points: the sample measure value synchronization, the communication reliability, and also the interoperability. So let's see with an example why this sample measure value synchronization is important. So here we have a transformer with 3 different windings, and we'll use 3 different merging units to collect the information of the current transformers. Every merging unit acquires the information, digitalizes and publishes it to the communication network, and sometime later then the protection device is able to collect or to subscribe to this information. Not all the values are going to arrive at the destination at the same time. So what the device is going to see is something like this: some values arriving first and others arriving later. And if the device doesn't do any special consideration and only compare these 3 values, then we'll see like a failure. But we know there is not a real failure in the system. This difference is caused because of a delay in the transmission or even in the manipulation in the merging unit. So we need to avoid this type of effect, and for that we use the sample measure value synchronization. So we set a pulse that we give to every single device involved in the Process Bus communication. So all the merging units start sampling the sample values at the very same moment. And this information of this synchronization pulse is also included inside the stream. So the protection device will receive the sample values plus this reference, and using this reference is able to align the curves. After aligning them, if there is no failure, real failure in the power system, then the device won't see any difference in the curves. To avoid problems in the system, if the synchronization is not given, the protection device will block the protection functionality. That's why from now on we'll be using redundant synchronization for our process bus stations. So remember, the first key point of the technology is the sample values synchronization. How we can achieve this? So let's first understand why there is a difference between the time synchronization and the sample values synchronization. The time synchronization is what we have done in the past in our station, so we give an absolute reference to the devices, so we are able to compare the failures and events and analyze the failures in the system. For this, we need an accuracy of 1 millisecond. That's good enough. In the case of the sample values, we don't need an absolute time. We just need a reference pulse. So we don't need this value to be synchronized to a global source. But this signal has to be high accurate, meaning we need to grant at least this microsecond accuracy for the sample values. How can we do it? So we have different type of mechanisms. For microsecond synchronization, we can use the PPS, or pulse per second, or the IEEE 1588 PTP, or precision time protocol. The advantage of the precision time protocol is that the same communication network can be used to distribute the synchronization signal, while for the PPS, or pulse per second, we need to have an independent network to distribute this PPS signal. To take away, process bus requires the synchronization of the sample values with 1 microsecond accuracy. This can be achieved using either PPS or PTP protocol. The SIPROTEC 5 devices support both of them. And when using the PTP, the precision time protocol, can be selected between 2 different types of profiles. The utility profile according to the IEC 61850-9-3, or the power profile from 2017. The synchronization is really important and therefore shall be redundant, meaning 2 master clocks should be available in the station to grant the high availability required for the protection systems. For process bus, we only need the relative reference, but for the complete station, we will need also this global reference for the fault analysis. So now we come to the second key point of the technology, the communication reliability. The sample measure values are defined as high priority telegrams. They are the main information required by our protection devices to be able to run the protection algorithms. So they need to come in a really secure manner and a really fast way. To achieve that, the standard defined the elimination of the TCP and IP layers, so this type of information, as in the case of the ghost messages, is transmitted using the layer 2. This makes the transmission faster, but then we cannot have any confirmation if the messages are arriving at the destination. For the ghost messages, we use repetition mechanism to ensure this arrival, but this mechanism cannot be used in the case of the sample measure values because they are transmitted cyclically. So we as users are to grant the reliability of the system, and for that, the seamless redundancy is required. So we have two options. We can use the PRP, the parallel redundancy protocol, or we can use the HSR, the high availability seamless redundancy. So let's see how they work. For the parallel redundancy protocol, every device is having two connections to independent networks, the PRP-A and the PRP-B, and all messages are duplicated. So every single message is transmitted through the line A and also through the line B. If the system is healthy, the destination device will receive two messages, and it should be able to recognize the repeated message and discard it. If there are also devices not supporting this PRP functionality, which need to be included in the network, it is possible using the so-called redundant boxes or red boxes. When a failure occurs, the device is still sending the two messages. One message is going to be lost, but the other one is going to arrive at the destination. And this happens without any type of delay, and that's why they are called the seamless redundant networks. So if we see the high availability seamless redundancy, the principle is the same. So every device is going to duplicate the messages, but now we are connecting the devices in a ring. So the message or the messages are just being transmitted through two different paths and being received in the destination device. If there is a problem in the network, then one of the messages is going to get lost, but the other one is going to arrive at the destination without any delay. And also in this type of configuration, the devices which are not capable can be added by using a red box. So remember, the second key point of the technology is the seamless communication required for the process bus. To take away is the seamless redundancy can be granted also for PRP and HSR networks, and the SIPROTEC 5 devices are supporting both of them. And now we come to the third point, the third key point of the technology, which is the interoperability. And when we talk about interoperability, then we need to talk about standards. The first standard defining the transmission of the analog values as digital values was included in the first edition of the IC 61850 standard in 2003. It was too wide to grant interoperability, and that's why 1 year later, so-called light edition was published to grant the interoperability. The light edition is not a standard, it's a profile of the chapter 9-2. And it allows actually the interoperability in communication, but it doesn't help when it comes to the interoperability in terms of functionality. So later on in 2016, the standard of the instrument transformers defined a couple of new settings and parameters which are required to grant this functional interoperability. It is about the context that the client device needs to have in order to properly understand the information being received as sample measured values. So this information is mainly received through the exchange files and kept as context in the protection device. If you see in this scheme, we have two different types of standards defining the communication between the merging unit and the protection devices. On one side, the chapter 9-2 mainly with the light edition, and on the other side, the Chapter 9 of the IC 6169. So let's refer specifically to the streams. The streams are the telegrams containing the sample values, containing the current and voltage information. So let's see the main difference between these two types of streams. The first point is the telegram format. For the light edition, we have a fixed format containing 8 values. 4 are currents and 4 are voltages, while for the flexible streams, it can freely define how many voltages or currents are included in one stream. The recommendation of the standard is having maximum 24 values in one stream. That's why they are called flexible streams. Then we need to talk about the sampling rate. For the light edition, was defined to have 2 different sampling rates, 80 samples per cycle for protection functionality and 256 for power quality or any application requiring a higher sampling rate. But this sampling rate is dependent of the frequency of the system, and that's something that the standard of the instrument transformers wants to avoid. So they defined 2 different type of sampling rates independent of the frequency of the system. On one side, we have the 4,800 Hz for protection applications, and then we have the 14,400 for power quality or other type of applications. However, when we use the standard of the instrument transformers, we will be also able to implement all the previous sampling rates included in the light edition that was thought to keep the backwards interoperability. And now we come to the sample value synchronization. For the light edition, it was defined that the way to achieve this synchronization was using PPS signal. Remember, this standard was released in 2003. And for the standard of the instrument transformers, is already allowed the use of the precision time protocol based on the IC 61850-9-3 profile, the so-called power utility profile. Also in this case, even using the streams of the instrument transformers, a PPS signal can be used to grant the backwards compatibility. In addition to these definitions, the standard of the instrument transformers included additional nameplates and parameters to grant the functional interoperability. And there is a complete chapter, the chapter number 13, dedicated to the merging unit as a standalone device. So what we have done now is, in the edition 2.1 of the IC 61850, we have integrated those elements mandatory in the standard of the instrument transformers, which are supporting the functional interoperability. Meaning, if we use the edition 2.1 of the IC 61850 standard, we can finally grant both types of interoperability, the communication and also the functional one. In addition to that, the edition 2.1 allows the transmission of the identification of the grandmaster clock. And that helps with the improvements of the availability of the system, because the protection functionality can be kept alive and operative even if the devices are being locally synchronized, given that all of them are synchronized to the same master clock. So that's an additional reason to prefer the edition 2.1 of the standard. So to take away with this interoperability topic, if you want to grant really the interoperability, then use the edition 2.1 when integrating devices from different vendors. If for any reason you cannot do it, then make sure running special tests that this interoperability is granted for your specific system. To take away, the IC 6150-9-2 Light Edition is a profile of the IC 6150-9 and help us with the communication interoperability, but not with the functional interoperability. This functional interoperability is addressed by the IC 6169-9, which is the standard of the instrument transformers. The edition 2.1 of the IC 61850 includes the mandatory elements defined by the instrument transformers to grant this functional interoperability. Therefore, the integration of merging unit and protection devices from different vendors must be done using the edition 2.1 of the IC 61850 standard. The SIPROTEC 5 devices support this edition 2.1 and can also support both type of streams, the light edition stream or the flexible streams according to the IC 61A69-9. So remember, the third key point of the technology is the use of international standards to fulfill this interoperability. And so we come to the end of this chapter about fundamentals. Thank you for joining us today and see you in the next video.